This is the second half of a two-part video on indeterminate forms and L'Hopital's rule. In the first part, we discussed quotient forms, 0 over 0 and infinity over infinity. In this video, we talk about the remaining indeterminate forms, the product, power, and difference form, and show how to calculate their limits involving these forms by first converting them to one of the two quotient forms and then applying L'Hopital's rule to calculate the limit. In order to use L'Hopital's rule to figure out the limit of a product indeterminate form, it is necessary to first convert the product form into one of the two quotient forms and then use L'Hopital's rule as we did in part 1 of this video. The procedure is straightforward. We write a product of two functions either as a quotient either in this form with the g going in the denominator or in this form with the f going in the denominator. If one of these two forms is a 0 over 0, then the other is infinity over infinity, and we can apply L'Hopital's to this. Now, which of these two you pick depends on one of two things. It's either easier to take the derivatives, as L'Hopital's rule involves derivatives, so pick the one that's easier to take the derivative of, or occasionally you may run into a situation where one of these forms works and the other doesn't, and so you have really no choice in such a case, as we will see in a minute. Let's take a look at an example where we figure out the limit of x times ln of x as x goes to 0 plus. Remember, this plus is just notation. Don't let it confuse you. X going to 0 plus simply means x goes to 0, but x is positive. And we need that in order to stay within the domain of ln of x, which is defined only for positive x. So positive x means x goes to 0 from the right. And when that happens, ln of x goes to negative infinity, and we get over here a 0 times infinity expression, or indeterminate form. We can change x times ln of x to a fraction by taking x to the denominator and writing it as a quotient, ln of x over 1 over x. Since ln of x goes to negative infinity, what we have here is an infinity over infinity indeterminate form, and we can apply L'Hopital's rule to this. Let me just point out that we could alternatively write this as x in the form of fraction as x divided by 1 over ln of x, which is the same thing as x over ln of x to the negative 1. And we could apply L'Hopital's rule to this. This will be a 0 over 0 form, 0 over 0. And the problem with this is that not only is the derivative a little bit more complicated because you need the chain rule, but also if you try it this way, you'll find that it is not very helpful. I encourage you to pause the video and check this for a couple of minutes, see just what you get. It'll be interesting. And then continue watching after you figure that a little bit out. Going back to the limit, I write 1 over x as x to the negative 1, calculate the limit by using L'Hopital's rule. The derivative of natural log is 1 over x. Derivative of x to the minus 1 is minus x to the minus 2. I can write the numerator 1 over x as x to the negative 1, and then it's easier to see how to simplify. I take x to the negative 2 to the numerator, becomes x to the positive 2, and then I can combine the powers. 2 minus 1 is 1, so I'll be left with just x. And the negative sign, of course, comes from the fraction. Limit of x as x goes to 0 from the right is 0. And that gives us the answer limit of x times ln of x as x goes to 0 plus a0. To convert power indeterminate forms to quotient ones for application of L'Hopital's rule, we use the logarithms. And the process for that is very standard. And this standard process applies to all three power indeterminate forms. We start with the function g of x raised to the power another function f of x, and we want to take the limit of that, let's call it y, as x goes to a. The process simply involves taking the natural log of both sides, that way to relocate the power using the property of logarithms. F of x comes out to the side. Now this expression is either a product form 0 times infinity or a quotient form already. If it is product, we convert it to quotient in the manner we just described. So we take this ln of y and apply L'Hopital's rule to find the limit as x goes to the quantity a. This process, of course, gives us the limit of the natural log of y, not y itself, which is what we are looking for. Because logarithm is continuous, this is not a problem. The limit can be taken inside a continuous function. We get natural log of limit of y. This form is good because now we can eliminate the ln using e. And the answer comes out e to the whatever we got using L'Hopital's rule. So that'll take care of the power indeterminate forms for us. The process that I just described may sound long and complicated, but its application to problems is actually quite easy. Let's consider an example like limit of x to the power x as x goes to 0 plus x going to the 0 from the right. Again, 0 from the right is necessary to make sure that we don't end up with a complex number like minus a half to the minus a half, which is an imaginary number. Now, using the standard process, let's cross that out. Using the standard procedure for relocating the power that we just talked about, gives us this expression here on the right-hand side. The x ln of x comes from the application of the logarithm, and the limit goes inside the logarithm and gives us this exponent here. Once we figure out limit of x ln of x up here as x goes to 0 plus, then e to that power will be the answer to our problem. Using L'Hopital rule, we found out a few minutes ago that x ln of x as x goes to 0 approaches 0. So the answer to the limit of x to the x as x goes to 0 is e to the 0, which happens to be 1. Just like that, and we are done with that problem. Okay, now let's take a look at these two limits side by side. They look kind of similar, but they don't have to come out the same answer. Let's take a look at the first one. As x goes to infinity, 1 over x goes to 0. So the first one is a infinity to the power 0 indeterminate form. Using the standard process with g of x equal to x and f of x equal to 1 over x, we get limit of f of x times ln of g of x in the power here. Next, we determine this limit using L'Hopital's rule. 1 over x times ln of x is ln of x over x. As x goes to infinity, ln does the same. So we have infinity over infinity expression here. Derivative of ln is 1 over x. Derivative of x is 1. And as x goes to infinity, 1 over x goes to 0. So the exponent comes out 0. And the answer will, of course, be e to that power, which is 1. Now, what about the second limit? In the second limit, 1 over infinity goes to 0, 1 over ln of x goes to 0 as x goes to infinity. So once again, we have a 0 infinity to the 0 expression there as well. We can go ahead and convert that to a non-power form using the usual strategy. So we get e to the f of x times ln of g of x. But notice that we get a surprise or bonus cancellation of the ln, and we are left with e to the 1. And of course, that's just e. This means that x to the power 1 over ln of x is a constant e, and therefore, to find its limit, we don't need L'Hopital's rule. Limit of e as x goes to infinity is e itself. Limit of a constant is always a constant. We don't need the L'Hopital's rule. So the second limit comes out just e rather than 1. I will talk about 1 to the infinity examples in the problems and solutions videos. So please check those for examples. A difference in determinant form, infinity minus infinity, is usually dealt with by changing it to one of the two quotient forms if we want to use the L'Hopital's rule. There is no rule of thumb like the power forms and the product form. So basically what we do is we take one of the and we combine the two expressions that go to infinity using algebra or whatever methods we think is relevant and see where that leads us. Okay, here's an example. Limit as x goes to 0, 1 over sine x minus 1 over x. Now, as x goes to 0, sine of x goes to 0. So 1 over that goes to infinity. 1 over x also goes to infinity, so we have an infinity minus infinity indeterminate form. Of course, the sign plus or minus will be different as x goes to 0 plus both sine x and x go to infinity with a positive sign. So the difference will be infinity minus infinity. As x goes to 0 minus, they both go to negative infinity. And so we get minus infinity plus infinity. But these two differences are as the same things. So the limits, the right limit and the left limit will turn out to be the same in this case. Let's combine the fractions, see what we get. The common denominator is x sine x. We go ahead and combine the fractions. We get x minus sine x over x times sine x. As x goes to 0, we get 0 in the numerator and 0 in the denominator, so we have a 0 over 0 expression, and therefore we can use L'Hopital's rule. The derivative of x minus sine x is 1 minus cosine x. For the denominator, we use the product rule. Derivative of the first, 1 times the second, sine x. Then the derivative of the second, cosine x, times the first. We get this expression. Notice that cosine of 0 is 1. So we end up with 0 over 0 again. We must apply L'Hopital's rule once again, one more time. Derivative of 1 is 0. Derivative of cosine is minus sine. x, and minus times minus becomes plus. In the denominator, derivative of sine is cosine. And for x cosine of x, we use the product rule. Derivative of x is 1 times cosine x plus x times derivative of cosine x is minus sine x, and that explains the minus. Now I have 2 cosine x here, sine x on top, and x sine x here. As x goes to 0, I get 0 on top. This term x sine x will also be 0, but cosine of 0 plus cosine of 0 is 1 plus 1, which comes out 2. It won't matter actually what this number is, because 0 divided by a non-zero number is always 0. And so that's the limit of this infinity minus infinity expressions. For more examples, take a look at the problems and solutions section, which contains a lot more exercises. And that's the end of this video for us.